Thanks, everyone. George and I from CompareTheMarket. So some of you, before we begin, I thought just to ask a question. How many of you put your hand up? And how many of you have used CompareTheMarket in the past? Okay. I only joined this company 3 months ago, and today is actually my last day of my probation. So people, before I was joining, I was trying to understand how does a company make profit. Think of if you go onto the CompareTheMarket website, it has a variety of products. Basically, for example, if you're quoting for your car insurance, you go through all those processes and you complete all those questions about your age, your postcode, and then you get directed to a price comparison page. From that on, CompareTheMarket has no visibility of whether or not you have purchased it. So the entire business is actually built on trust, meaning that CompareTheMarket rely on the partners sending us the sales information. That sales is purchased through CompareTheMarket. So, which means it kind of result, you have so many partners, so many insurance brokers. So that those sort of information comes back to CompareTheMarket. That's a lot of information and a lot of external data sources coming in. I'll skip this one. Basically, I'll be talking about how we're actually handling the actual problem that we kind of encountered during our work on one of the projects. And then George is going to talk about the platform, that how we doing model development and the deploy model, the entire workflow process. So we have already mentioned about data at CompareTheMarket. Volume. Well, first question, we kind of answered it. Yes and no. They use Meerkat as a promotion, so it's almost spending money to make money. In terms of data volume, the company holds around about 28 million customer information. From sort of like, say, the active customer in the last year is about over 5 million. We have a lot of user journey information. That's basically saying majority of the time you don't just go there and having a quote and purchase it straight away. You tend to go back and change something. That's another user journey being created on the back of it. In terms of velocity, I assume that majority of the people here will only probably purchase one product through CompareTheMarket, with home insurance or car insurance. Probably other products you don't even know that CompareTheMarket actually does a range of products from energy, from pet insurance, bike insurance, wine insurance, so on and so forth. We have talked about the data variety, which is quite high. We're getting a lot of external data sources, which on top of what we already have, which is customer information, as well as user journey information. So the problem that the project we are working on is called next best product, meaning that we hope to identify at any given time that which product is the most interested product for each individual customers. We took the multi-neighbor classification approach. Many of you probably have used it in your work or previously. In a nutshell, think of multinomial modeling as a particular case of multi-neighbor classification. The reason why that we want to kind of mention this is that we hope that for some of you after the meeting tonight, and you have learned something that you can potentially apply it to solve similar problem with similar techniques that we propose. So basically,
multiple matches.
That's never happened.
No problem. Anyway, we are trying to learn all those 7 products simultaneously. Think of that in other problem when you do imagery recognition. Imaging could be about landscape, or there could be a boat in that image. So that image could be a boat, so on and so forth. We thought if we use the same approach, that would allow us to kind of be able to do all our predictions simultaneously. Therefore, we can, from that result, identify which one is the most likely product for each single individual customer. So some of you may have questioned, how does that differ from multinomial multinomial modeling? In some sense, it is not. But however, if it is not, because think of that, if you're assuming all your target neighbors are independent and you model them individually, you're essentially getting a multinomial model. However, that's not actually the case. Majority of the time that all those targets, they have correlation among them, meaning that if you treat them independently, potentially misleading, which is not a good thing. The data we worked with is around about 20 million data points with around about 366 variables or features. It's about approximate 15 gig of the data. The data kind of construct in a way that allows us to take into account of potential seasonalities, which means we know that throughout the year, at a given point in time, if someone that has already quoted on a car insurance on a particular period of time previously, we would be expecting that if that time matches the time period that we're currently doing this scoring process, we would be able to, at least we would hope that customer would have a higher probability to quote or come back and look for that product. So what's the performance? The model performance is kind of built on the back of a combined of techniques. That is Ensemble Classification with enhanced data that we work with. I'll point out what I mean by enhanced data. That's exactly the title we're seeing at the beginning, which is imbalanced. Imbalanced meaning that for some of the product, actually majority of the product, there's so little positive targets and a massive amount of negatives. That creates a problem for the model prediction. So we're handling that through simulation, basically sampling on the positive samples. Some of you may have a question about why don't you downsample the negative negative data points. The problem we had is if we look at the number of features we're considering in the model, that for some products, if we say take random example from 500,000 data points, for some products the positive targets is actually less than the number of features we currently look at. So even we can downsample the negative data points, it wouldn't actually help us on this problem in particular. However, if some of you apply the same technique to your specific problem, if this isn't an issue, you can try and combine both downsample and oversample. Which could potentially allow you to improve the model performance. There's another term which is the ensemble classified chain. I'll talk that in the next slide after pointing out the model prediction. If we take in the bike model as example, basically from the test result or the validation result, we see that from the 10%, top 10% or top decile, if you like, it covers 70% of the actual people who have quoted on bike insurance. That basically is saying that we can focus on our marketing campaign energy onto those subset of customer. We can still ensure the same amount of conversion that we can get, at least on this product specifically. If we go to the next slide, probably many of you are unable to see, just to give you an overall view on the results we have here. So this is individual model performance on those 7 products. Bike is over here, the top second one. And if we look at energy, top decile gives us nearly 60%. And then if you look at wine, top decile give us over 60% of the lift, which kind of shows the method works. The model, at least individually, performs really well. So what's the overall accuracy? Still, if we look at 96.8, that's pretty good overall accuracy. In terms of all those assessments, we can safely say the approach we took allows us to not only be able to handle the massive imbalance within our data, but also gives us pretty good model performance. Sorry. Now, Ensemble Classified Chain. Basically, as I was mentioning at the beginning, that multi-neighbor classification, the application of that has been on a lot of other things. For example, email, bioinformatics, music, so on and so forth. If you want to read more about sort of different approaches within multi-neighbor classification, there's a pretty good reference by Jesse that they kind of outlined there are two, in general, there are two types of two ways of doing multi-neighbor classification. The first one is problem transformation, and the second one being algorithm adaptation. The approach we took is actually the problem transformation, which is also sometimes called the binary relevance. We built on the binary relevance, which allows us to have the ensemble classified chain. So by classified chain, meaning that we'll pick one product first. We'll learn based on the data we have, and then we'll make a prediction on that product specifically. That prediction will be added into the original data set as an additional feature, and allows us to making learning or prediction on the second target that we are trying to learn, so on and so forth. Hence, it is a chain. The ensemble, some of you probably already realized, okay, how do you decide what order we are going through? We can start from product 1, product 3, product 4, so on and so forth. We don't know which is the right order. Therefore, we're creating an order process. So meaning that if we are able to take what we have built up on the classified chain, and we're filtering a particular order, and then the chain will take into that order into account, and then making the learning and the prediction. So we can do that many, many times. So the order will be different. For example, if you have 7 products, so that's basically 5,040 different orders across 1, 2, 3, and then it could be starting from 2, 3, 4, so on and so forth. Obviously, going through all those orders is going to be computationally challenging. What you can do in sort of like a real application is try to testing with a smaller data set and with a small amount of ordering that you have stimulated, then try to test in the performance. If it works, you can basically increase your data points, which, as a matter of fact, when you're doing learning, a good learning, you only do it once. If you're trying to build a batch process on the back of it, you only do the learning once. As long as the learning gives you the best prediction on what you're trying to do, and then that would be the final learning that you're going to do. So we somehow got lucky with our approach, simply because that if we're considering we are over-simulating on the positive data points. Suppose that all the data points have a very high concurrence rate, meaning that your simulation, product by product, will change in the underlying distribution, or at least on your target data points. We got lucky because the sort of overall concurrence rate is quite small. However, we should still take that potential correlation among targets neighbors into consideration when we actually working with multi-neighbor classification. Right. This project is still in progress. What we hope is that with all, for example, the ensemble algorithm that creating that order, which this order will pass into what will pass into the classified chain, where the data that classified chain has used has already been simulated, enhanced. All those processes would allow us to kind of run target by target in a sequential manner. And then at the end of the algorithm running, we can doing aggregation on all the prediction that we have. So to help kind of speed up the time, what we can actually improve is to suppose you're generating 100 orders, meaning that if we can parallelize that 100 orders into 100 different calculations, we can potentially speed up that process. As I was mentioning, the work is still in progress. Once the final algorithm that is in place, George and I will definitely share with more wider public, because every one of us, if we are facing the same problem, we can use the same technique and apply it to solving the problem that we have in the project. Okay. We are still researching a way how we can simulate when there's very high target neighbor concurrence. We will continue to work on the ensemble classifier chain. That would allow us would allow us easily using any conventional classification algorithm you're currently using. We'll try to optimize the algorithm performances. At the moment, we know with all those simulation and all those sequential calculation, it's very time consuming. So for that, thank you, and I'll hand it over to George.
So I'm a senior software engineer. I'm working closely with the data science team. I'm responsible for the production version of all the data scientist projects. So we have different types of data science projects. One type is that those we're running, let's say, offline with data that we're collecting from all the databases. And we have also a new, really ambitious project, which is the personalization project. So CompareTheMarket is a price comparison website. We have users that are visiting the website, are selecting a product, they're filling some forms until they get a list of quotes, then they click in a quote, and then they go into the insurance. company, and then probably they're buying something they're buying the product that they actually chose from the CompareTheMarket. So we're thinking we are very strong in the marketing side. We have a very strong marketing team that is doing many campaigns, and this is where the offline data science algorithms are giving us which segments of the user base, of the customer base, of the user base in general, to target in order to send really target campaigns. But we wanted to do something quite different and quite interesting project. So our interaction with the user is interacting with the company in general through the website and through the mobile client. So our approach in the personalization project, the goal mainly, is how to provide to the user a more personalized user experience. So we have a more personalized user experience while they are interacting. So our users can be anonymous in a way that they can add garbage data through the journey, but they can also log in. So if they log in, we have a better understanding of their actual profile of the user. But we also need to target those that are choosing not to add all the real data or all the real personal information, like the name, the username, even the age sometimes. So we like somehow to enhance and engage our users during this process, because the process is quite boring after a while when you have to fill so many forms in order to get an actual quote list. So we have seen that many users, for example, they said, okay, I'm not going to do it now, I'm going to do it some later time. So we're trying somehow to understand our users and try, when they are following this journey, somehow what is making them to quit early. So for example, there is some question that we can rearrange the questions in order to make them go forward on this journey and actually get the list of quotes. It will be really helpful. The project should be in real time. This is one first challenge we had, because while we are doing this, we need not only if we have the user profile, like the user has actually logged in, we can have more data, but we like also at every stage of this process, of this journey, to be able to make a personalized action, something that will make him to continue. And this is quite challenging in a way, because we need to have a real-time data science algorithm, and requires really from the computational perspective, but also from the platform perspective, really innovative solutions in order to be in order to provide this quality of service that we are looking for. So when we were writing the requirements for this project, the first, of course, requirement, the most important, was the real-time decision engine. The real-time decision engine. So we're planning to build what Sky described earlier, is one part of this personalization program. So the next best product is going to give us predictions about if someone, a customer, is going to buy another product. But this one is only one project, one part of the personalization program. We like to have an actual action at each stage. And these actions can be many things. Can be some banner, can be not showing all the questions, so a subset of the questions. So we like to be very, very, having a dynamic journey. Right now it's very static. We have a number of questions, it is already written down, and it's going to have the same questions no matter what, who is the user, where he's coming from, or what other data we can have from him. And also our goal was not to annoy users somehow, or not to make it a creepy system that he thinks that we're actually tracking him online, or that we are having so many data, we know everything about the customer. So we need to be really careful on that part, because users can be really scared about these kind of things. And also, from the platform perspective, this will be a really flexible system. So we're thinking that the data science algorithms we're going to have is not going to be very static. We like to play with many algorithms. We like to evaluate them. We like to assess. We would like to run alpha beta testing. We would like to have a really flexible system that ideally the data scientists are going to build something and without really a lot of development time to be able to deploy a new strategy, a new algorithm. So we had to deal, when we were starting building this, we had to deal with a number of issues, mainly from the legacy of the systems. Mainly the website is, the production data of the website is using using many SQL servers. And also we have SQL data warehouses. The data team owned a Hadoop cluster that we were collecting all the data from all the databases, and we're running typically analytic jobs. And these, there were jobs written in Pig, Hive, HBase, and coordinated by Uzi. We had also, for some projects, we have using MongoDB. So this, it was mainly the technology stack that we were using before starting this project. So when we were starting talking about real-time, and we realized that we have Hive and Pig, that typically most of the jobs were taking hours to complete, we had to figure out ways of improving this, because we're going to use not only for the real-time scoring and the real-time personalization project, we want to also to have analytic data. So mainly the challenges that we had to consider before starting this project. So we have lots of unpredictable jobs. We had jobs that were running for hours, or some jobs that were finishing early, some jobs that were finishing late. We have some crashes for data quality. We have data quality problems, and also the data were everywhere. We're in a data warehouse, they were in Hadoop. Some of the data we had in Hadoop, the Hadoop cluster actually was in a data center we owned. So, and we had also space issues, performance issues. So it was really, really difficult to find out how we're going to do a real-time system using these legacy systems. So we had 3 stages. We decided that we need to first migrate, we have the first migration stage, the second migration, and the third one. The first migration stage, we were trying to move all our systems to AWS. So we had to migrate all of the on-premise cluster we own, all the jobs that we're running there, to run them on Amazon. Also, the other approach that we used that was very, very useful, because the data were everywhere, and sometimes they are outdated data, sometimes they were historical data. We had somehow put the data in one place, and the best place we can put them was S3, and is S3. So we put all the data in S3, and we keep putting data in S3 right now. And also we used EMR clusters to start rebuilding some of the workflows we're having in the old Hadoop cluster, and we start using EMR and Spark, rewriting some of the old Hive batch jobs using EMR and Spark. So we have just moving to these 2 technologies, we're able to speed up the analytic process for a couple of hours to sometimes minutes for some cases. The other approach, the old data scientists the old data science team were using just SPSS or SAS. So with the new team, we try to prototype all the algorithms in R and Python for the development, and for the production, we're going to use Spark and Scala. So some learns that we learned during this process, always when you try to migrate lots of things at the same time, it's very, very painful and very, very time-consuming and frustrated. The period is very frustrated, and everyone was frustrated mainly because we tried to migrate the platform, the cluster, the business logic, the workflows, and everything, and also moving to a new language, which is some of the members of the team they didn't have actual experience with Scala. So we try to have an incremental approach. So we try to find which jobs were really critical for our purpose, and try to create independent jobs in EMR clusters. So one job is in one EMR cluster and one Spark application, and get the data from S3, process them, filter them, clean them, maybe find some correlations or whatever, and then store them back to S3. So we start moving towards this methodology. And also we're trying to minimize the dependency. We had a really big dependency hell on the Hadoop cluster that were thousands of tables and data are coming from everywhere. But with our approach, we try to have really clean models, and at each stage to be able to reason where the data are coming from, which was very, very difficult. It was very difficult to reason someone, we have this table, where the data are coming. We can maybe find the first step, but when you go to the second step, it's becoming exponential in a way of actually identifying that this specific row is coming by combining 3 other rows from different tables. And we tried also to move to a more immutable process, which is immutable in a way that inputs, outputs, there will be nothing between the inputs and outputs. So we have a predictable result every single time. If we run the same job for the same input, we're going to have the same output, because it was something that was not happening before, and it was very tricky to overcome these difficulties. And the good thing with Scala and the approach we used, typically before we're using just data files. We're trying to, most of the times we were working with data files, were CSV files, there were Parquet files, there were so many different formats. So we moved from thinking about raw data files to moving to objects. So we start building our models as classes that we're going to map them from the raw data to the actual classes, start working with the classes, and then when we're in the final stage, which is writing the data back to S3, then we're going back to files again. So we start having more and more things on the classes level, which is much easier to reason. We have the type safety, that's something we're missing with raw data, and also we're able to do versioning. So we didn't have situations, we have situations before like having data with different fields, or we haven't done any proper filtering. All of these problems are solved just by mapping those raw data files to actual objects. So in this real-time personalization, all of this is the first stage. We have to migrate all of this data in order to start running analytics and batch jobs in a really fast way. So the second stage, the plan for the second stage is how to get real-time data. So typically real-time, when we're saying real-time data, when we have when a user is interacting with the website or the mobile client, is creating events. Those events can be filling a form, or moving the mouse, or clicking this or clicking that, so it's all the interactions. We're collecting all this data as events. Those events we send the events to a message queue called Kafka. So all the events eventually are going to Kafka. This is the architecture, the new architecture for the personalization engine. Mainly, we have the user, we have the website, we're collecting all the events and we send them to Kafka, and then we're using Spark streaming. We're using Spark streaming to process, consume events from Kafka, apply the transformations and the processing it is required, and then sending the decision, mainly, to another service, we call it Personalization Manager, for a specific action. So, for example, the user is going to the website, is going to the first form, maybe he's moving the mouse somewhere in a form, he's filling one field, then he's clicking next. All those events will go through Kafka to the Spark streaming. And the Spark streaming is going to decide every single time. The decision can be do nothing, or can be show some message there, or for the next step, don't show this field because we have found out that if we show this field, typically users are quitting, for example. So the most challenging part in this approach, in order to do it in real time, was how to use data from other services, because the company inside the company there are so many web services. There is a typical microservice architecture. So we have data in different formats. For example, if some user specified, don't contact me for any reason, or I'm unsubscribed. So probably it's in some list somewhere. So the problem is how we can get the data while the Spark streaming job is running, which is a very difficult problem, because typically in Spark jobs, we load some data from a database, we load some from some files, we do something, and then we write it somewhere else. In the Spark streaming, we keep having a collection of RDDs. RDDs are the abstraction Spark is using and data frames for the new version to abstract the concept of the data. So the problem of combining data from different web services, it was a very difficult problem. This is where we came up with a new concept, which is, we call it reactive RDD. A reactive RDD is a typical custom RDD. It's a custom version, an extension of RDD that is giving us a way of abstracting a number of web services, a number of data sources, and having the same API as the typical RDD. So in a way, we can have a typical sources from a Spark application is a database, some text file, some CSV file, some compressed file, or some Parquet file. But we're interested about some kind of virtual data source that is actually the result of calling a web service. So this abstraction is formulated through this reactive RTD. So the reactive RTD approach is inspired by the functional reactive programming approaches in general, and you can consider it as an abstraction of multiple web services plus the caching in a transparent way. So for having different, for example, we like to, if we call 3 services to get some data, and we're interested about the first one, we don't interested to get update data every minute or every second, or we can say it's safe to have a cache version of this. This RDD is going to provide us an abstraction of the web service, and also is going to provide a cache policy that the data are going to get either from the cache or calling the actual web services to get the data. But all of these are hidden from the developer and is having to deal with typical RDDs as any other Spark job. So it's very transparent and it's very flexible way of getting and combining data from many different types of resources. So typically there are RESTful services, but apart from the RESTful services, you don't have to deal with timeouts maybe, or if there are some other issues like there are some delays. So all of these are abstracted through this reactive RTD. It also solves the problem of updating data on the fly. While the Spark streaming job is running, and we are processing data messages from the Kafka message queue, if we need to get some data to take a decision, this decision is based on some data we have in another place, we don't have a problem when we're going to, if the data are outdated or not, if we need to get an updated version, because this reactive RDD is going to give us the up-to-date version of it. So our platform is a work in progress, but from the first start we're able to process tens of thousands of messages per second, and even with Spark, which is not supposed to be an event, it's not an event processing framework in a way, because we have a window, but the results we're getting are very convincing, and we believe that the next steps, which is mainly how to make this as a service, like use Docker, Kubernetes, and also we have to do that mainly because we're using native machine learning libraries like XGBoost, which is a C++ library. So there are other libraries we're using. So it's much better to have a more control on the deployment. And also, it's quite interesting for us to investigate different policies for caching, because different data, maybe some data are changing every day, some data are changing every month, so we don't have to minimize the cost. We need to can have different policies in general. So more or less, this is the architecture we are building, and the personalization project is going to be the framework for deploying many real-time data science algorithms, and we believe that we'll have really good results in the future.